Thank you, and thanks to the organizers for inviting me. So yeah, I'm going to talk about formalizing SNARK, Soundness, in a language called Lean. I'll talk mostly, I think, about my previous work formalizing a type of SNARK called linear PCP SNARKs. And if I have time, I'll also get into some more recent, more ongoing work on formalizing polynomial IOP type SNARKs. So just to start things off, I'm going to provide a list of reasons why the things that I'm going to talk about might be a good idea. So what does it mean to formally verify something? To formally verify something is to basically prove to a computer that what your code does is correct. And so there are a variety of reasons you might want to do this. One reason is that we're doing this for cryptography. There are a variety of reasons we might want to do this for SNARKs in particular. One reason is that SNARKs are cryptography, and cryptography is used for security. And so it's good to have a high level of security if we're doing things with cryptography. Another reason that it would be good to do for SNARKs is that SNARKs have a sort of adversarial model, which we'll get into, where to prove soundness, you need to prove it for all of the adversaries you model. And this is something that's hard to do just by spot checking or with other techniques in formal analysis. A third reason is that the math behind SNARKs, I think it was called like moon math, right? It's hard math, so it's hard to be confident in. And to this point, there have been bugs that have been encountered in previous SNARKs that have been deployed in practice, a variety of bugs of different kinds. Getting more into the more philosophical range, it might be nice to combine these verified SNARK circuits with verified SNARK circuits, which I think we'll probably hear about in the very next talk. It might be nice to combine these with verification for the protocols to get end-to-end proofs. It would also be good to sort of, do a systemization of knowledge for SNARKs using these sort of ideas to sort of synthesize math and computational thinking. It's a good test of the software. And also, it's just on sort of the most broad level, it's just good to explore the synergies between these two related topics. So the first section of my talk is about linear PCP SNARKs. The most famous example of a SNARK of this kind is the Groth16 SNARK. So it's sort of older, but still very broadly used kind of SNARK. Just to begin with a bit of discussion of the reasoning for the security of these SNARKs. So the linear PCP SNARKs, at least in our development, are proved secure in the algebraic group model. And what this basically means is that there's something called this bilinear elliptic curve pairing, which is a sort of abstract mathematical object. But the key rules that are thought to hold for this object is that you can have field elements that belong to one of three groups. They can belong to group 1, group 2, or the target group, group T. And there are only very limited rules that the parties participating have for manipulating these encrypted field elements. So they can add field elements from one group, or they can multiply them by constants. And the only way that they can multiply the elements is to take an element from group 1 and an element from group 2 and transform that into a product, which then inhabits the third group, the T group. So to walk through the steps of a linear PCP SNARK protocol, it will always go something like this, and hopefully you'll see that the AGM structure is actually sort of what forces this to be the case. The way it proceeds is that there's a trusted third party that samples some random field elements. They construct what's known as a structured reference string, or SRS, as encryptions of multivariable polynomials evaluated at these elements. Then the SRS is given to the prover and the verifier, who are the parties who are participating. The prover will then complete the proof for this SNARK, which is going to consist of making linear combinations of the elements that they received. And because of the AGM, that's essentially all the prover is going to be able to do. They're going to get a proof pi out of this process, which will be sent to the verifier, and then the verifier will do some operations with the elliptic curve. They'll construct some, they'll construct some group elements of their own. They might compute some pairings, which means they're going to do the multiplication operation. And finally, there's going to be some equality checks at the end that guarantee that certain things are equal. And so the main takeaway I want you to get from this slide is that all of the operations that are being carried out in this list of steps, they all preserve the fact that every piece of data that anyone ever touches in this protocol can be thought of as a multivariable polynomial over the initial samples that were sampled in step 1. Everything is essentially a multivariable polynomial from the perspective of the parties here. And this turns out to be very convenient for both constructing these protocols and then proving the protocols sound. Basically, what we have is that because everything that the prover or verifier ever touches, it's just going to be an encryption of a multivariable polynomial over which, or you could think of it as an evaluation of a multivariable polynomial where the value that it's evaluated at is random. Basically, what we can sort of conceptualize this as formalizing the entire structure of the SNARKs in terms of these manipulations of the polynomials that underlie these field elements. And this sort of relies on a theorem called the Schwartz-Zippel lemma, which basically says that if you have two polynomials, those polynomials are going to turn out to be equal but with very, very high probability if you evaluate them on random elements and the evaluations turn out to be equal. And the nice thing about this is that it basically lets us avoid thinking too much about the underlying cryptographic assumptions. It just lets us work in this more abstract model where everything is a polynomial, and we just have to make reasoning about polynomials. And it's good that we only have to make reasons about polynomials because there's a further set of mathematical techniques called Grobner basis methods, which basically allow you to take a list of polynomial equations and automatically determine if some further polynomial equation is true. And now, so these Grobner basis methods are not necessarily always efficient, but I think what we've sort of shown is that using some heuristics, it's the case that they can be made efficient enough to work automatically for the popular SNARK schemes like Groth 16 and various variants of it and various predecessors of it. So now I'm just going to walk you basically through how this automatic proof can go. I have this sort of toy example of a SNARK here. It's not even really a complete SNARK. This is just a simple example, which is trying to prove the statement A times D equals E or B times C is equal to E. And here we have the random field elements here are alpha and beta. And I also have alpha sub 1, beta sub 1, alpha sub 2, beta sub 2 for the presence of those field elements within these cryptographic groups. And what's going to happen is that we're going to have A times alpha plus B times beta as this proof element. That'll be multiplied by C times alpha plus D times beta, and it'll be checked against E times alpha beta. And so what we need to show in terms of the soundness is that this implies the conclusion. So now I'm just going to go through the sort of steps of the reasoning, how this looks when you're actually carrying out the proof in the interactive proof assistant, which sort of, at all times during the use of an interactive proof assistant, you have a list of the assumptions that you have, and you have a statement of what the goal is that you're trying to prove. So we start off with this multivariable polynomial equation, which I won't read out, but you can see on top, and we're trying to prove the thing on the bottom. A prime and B prime here are the sort of assumed that they're the sort of derived values that we sort of impute from the prover by virtue of their participation in the AGM protocol. The first thing we do basically is to isolate coefficients by running the distributive law. Hopefully you can sort of inspect these two equations and see that all that's been done here is to apply the distributive law. The next thing we do is to observe that two multivariable polynomials are equal if and only if each of their coefficients are equal. This is sort of the extensionality principle is what it's called for polynomials. So on the left-hand side, we have A prime times D plus B prime times C is the coefficient of alpha beta. And on the right-hand side, we have E, and so that's what we get for our equation. We get something simpler for the alpha squared term and the beta squared term. And so now we have this list of assumptions. And this is the point at which we can start applying sort of Grobner basis methods. But what we do to sort of simplify things before we begin to apply Grobner basis methods is we notice that we can do this sort of factorization step. So we have, for example, A prime times C is equal to 0 here. Well, because we're working over a field, A prime times C is equivalent, that being equal to 0 is equivalent to A prime being equal to 0 or C prime or C being equal to 0. And we can do a similar thing with B prime times D as well. And so this is, this is a step that is a heuristic. It's not necessarily, it doesn't necessarily have to be done in evaluating a Grosvenor basis. But because of the way that SNARKs from the literature tend to be constructed, they tend to be constructed in a way that makes the proof easier. And one way that is done is to make it so that it's very often the case that we have a product of things that turns out to be 0. And so when you analyze more complicated SNARKs like Groth 16, you'll find many of these instances where you can carry out this factorization. And so now that we have these new assumptions, we can move on and we can sort of do casework. We can split an OR into 2 separate cases, and we can simplify the things that are equal to 0. We can simplify those away, and at that point, we would basically be done with the proof. So that's the sort of high-level walkthrough of how the automation can work that basically only relies on these sort of manipulations of polynomials to carry out this formal proof. So with my last few minutes, I'll also talk a little bit about what it takes to formalize slightly more modern SNARKs, right? Polynomial IOP SNARKs examples include Planck or Marlin in the case of the work that I've been doing with Bertuche. So polynomial IOP SNARKs are sort of a different structure of SNARK. They are sort of created through the combination of a variety of techniques. There's this interactive oracle proof, where there's this prover and the verifier, and the prover is sending polynomial commitments to the verifier, and the verifier is sending back randomness. And at the end, there's this sort of opening procedure where the verifier gets all these polynomials. It only has commitments to the polynomials, but it can nevertheless inspect the polynomials with the help of the prover to find out what the evaluation of those polynomials is at various points. The sort of challenge with formalizing polynomial IOP SNARKs, as opposed to linear PCP SNARKs, which are much simpler, is that polynomial IOPs are structured more as sort of these programs where, at the top level we have the whole protocol, but there are sub-protocols that get recursively called all the way down to the sort of basic elements of the polynomial commitment scheme. And so the approach that we've taken to formalize these kind of SNARKs is to use sort of this monadic programming paradigm from functional programming, where we provide this sort of API for all of the low-level operations that we can carry out. And then the nice thing that we can do is, taking advantage of the fact that a polynomial IOP protocol has these various components, right? They have the component of the prover. They have the component of the choices of random samples that the verifier carries out. They also have the components of these point queries and the checks that the verifier does to decide whether the proof is successful. Basically, all of these individual points can be implemented themselves using this monad technique. And so this turns out to be a very nice way of being able to sort of specify a SNARK in a more sort of declarative, imperative programming style, and still get out the main features of the protocol that we need to then go on and prove the soundness. So that's basically a description of the sort of 2 projects that I have. Happy to take any questions about this.
How does your work compare with other efforts at formally verifying ZKPs or like even MPC protocols? Like, is it just a matter of applying these techniques to every scheme, or maybe your approach is fundamentally different in some other way?
Yeah. So most of the work that I've seen that works on proving zero-knowledge proof protocols is, I guess, is more on the circuit level. I guess there are a lot of smart contracts that are that have circuits in them that use zero-knowledge proofs, and those all need to be verified. And so there's like a lot of work. I mean, I'm sure we're about to find out, like developing tools for this sort of thing. When you get into the sort of work of verifying the protocols themselves, it turns more to the sort of mathematical details. So for example, there's a lot of work that has to be done about low-level polynomial reasoning to prove the Schwarz-Zippel lemma, or to prove, for example, the sum check lemma is another sort of basic technique in this field. And so I guess what I am trying to do here is to sort of extend the sort of mathematical basis to sort of, we have to make a bridge, right, from the sort of mathematical basis to the thing that allows us to then touch the circuits and then move on to verifying things end to end. So I think I'm sort of in the middle between those two.
What
parts.
about like the work, this machine checked ZKP for MP relations? Is that also verifying circuit? I thought they are verifying the protocol itself.
Sorry, say the name again.
CCS 2021, machine checked ZKP for MP relation.
Right. So that particular work, I think, is handles. So it's also the case. It's also the case that there are some works that deal with non-succinct zero knowledge proofs. I think that might be an example of one of those. So in this case, I'm dealing with succinct protocols, and there are some differences there. I think with the succinct protocols, I'm trying to focus more on the details that allow the use of succinctness, which is more of this polynomial reasoning. With the sort of more, for the less succinct protocols, I think it will probably have more to do with the high-level reasoning about whatever technique they happen to be using. But I think there will probably be some differences there.
So are there any useful insights, or is it just a matter of taking, no matter whether it's succinct or not, just taking the scheme and code it up in one of the formal verification tools? Like maybe some people use Lean, but I've also seen people do it in like other proof systems.
So I think that the one key useful insight is that all you have to do is code it up, and then once you have coded it up, you might be worried, okay, how am I actually going to proceed with the proof? What I'd like the takeaway to be is that there are automated procedures that will help you with this part. Because while that reasoning can be complex, it ultimately belongs to a class of mathematical statements that has automation built for it. So for example, useful in Lean is the polyrith tactic, which is this automation procedure that deals with Grosvenor bases. There's also NSATs for the Coq language. I'm not too sure about other languages, but I think that it's possible to build this sort of automation. Yeah.
So do you have any insights for making this kind of proof more scalable for the future? Like after this experience of trying to code it up in Lean, like is there some new tactics you can develop that helps with proving things like this?
Making the proof of the soundness more scalable, or the proofs themselves more scalable?
Just the effort of I guess the effort of I guess one big challenge for this formal verification tool is it requires a lot of expertise and human effort, and it's not very scalable in that sense, right?
Yeah, certainly.
The real world protocols are complex, and it's also not just the protocol itself. There's also application logic surrounding the protocol. So yeah, so it's definitely going to be difficult to get to the point where you can simply formalize the protocol and then you just hit go, and then the whole thing is proven for you without you having to apply any additional details. I think the jury's still out maybe a little bit on whether advances in machine learning and some of the techniques that people are trying are going to help with this and make it possible for this to totally be done end to end. But whether it's the case that happens, and in which case it will become much easier to sort of formalize these protocols, or whether it's just the case that you have to hire someone who's an expert in formal methods to do this for you. Hopefully, in either case, this sort of work will be helpful in facilitating that. Okay, I think that's all the time we have. Thanks for the questions.